This is Math 5700 Lecture 41. I'm going to continue discussion of section 7.4 in the text, which is about covariance. So let's recall what little we did last time with covariance. We defined it in the following way. The covariance of a pair of random variables x and y is by definition the expected value of x times y minus the expected value of x times the expected value of y. Okay, and this actually will give you, this actually tells you something about whether or not the random variables are dependent. So here's a fact that if, and it's obvious from the definition, if the covariance of x and y is not zero, then it follows that x and y must be dependent, meaning they're not independent. Okay, so there are additional properties of covariance, which I've listed last time. So let me list them again. So property one is that the covariance of x and y, it's symmetrical in the variables x and y. Property two is that if I take the covariance of x with itself, I get by definition the variance of x. Property three is if I take the covariance of a number a times x and pair it with y, then I can bring the a right through to get a times the covariance of x and y. By the way, you can put that a in the other variable because of the first property. Likewise, if I take the covariance of x plus y with another z, it breaks up as the covariance of xz plus the covariance of y and z. So these two properties here, these last two, are called bilinearity, linearity in each of the variables. Okay, so, and then we can actually extend the bilinearity to any number of things. We can take the covariance of some sum xi, sum yj, any finite sums, and this breaks up as a double sum over I and j of the covariance of each atom, xi, yj. Okay, so these are basic properties that the covariance satisfies. There are a couple more coming. I'm just running out of space on this slide. Here's another one. If I take the variance of a sum of two variables, x and y, and add them, we can compute that now in terms of covariance. This is the covariance of x plus y with itself. And then we can break it up as the covariance of x with itself plus the covariance of x with y plus these are from the properties above in the previous slide, yx plus the covariance of y with y, and this can be rewritten as by using the properties, the variance of x plus the variance of y plus two cross terms, which can be written as the covariance of x and y. So in particular, if x and y are independent, then the covariance of x and y vanish, then we get the variance of x plus y, equals the variance of x plus the variance of y if they're independent. So you need to assume independence here. Okay, so so that's cool. I like that. Okay, so what other properties? Well, more generally, if x1, x2 are a sequence of n random variables and they are pairwise independent, then the variance of x1 plus all the way up to xn is equal to the sum of the variances. So that's an extension of what I just did before with two of these. Okay, so here's an application of all of this, or an example. Suppose I have x is binomial, a binomial random variable of type b and p. So it's a discrete random variable. And recall that we know that p, the expected value. Okay, so let me write it like this: x is x1. This I did on my last lecture. I wrote it as a sum. So we have n Bernoulli trials, and x sub k is 1 if success occurs on the kth trial. When I say trial, think flipping a coin, a biased coin of probability p, and 0 if not. And then we know that p is the expected value of each xk for all k. So so now let x1, so then note that each xi is just the result of performing a single experiment. The experiments don't interact with each other. They're independent. In fact, x1 through xn are independent, identically distributed. So I, D, random variables. So now let's compute the variance of x sub k for each k. Well, that's by definition the expected value of x sub k squared minus the expected value of x sub k, that quantity squared. But notice that if you go back to the definition of x sub k, you square it, you get x sub k again. It doesn't change when you square it. So therefore, that tells me that this variance that we're computing is x, the expected value of x sub k minus the expected value of x sub k, that quantity squared. But we know from what I wrote up here that I'm boxing off now that this is p minus p squared. So that's the variance of x sub k. Now, since the xi's are identically distributed and independent, in particular, they're pairwise independent. Any pair are independent. We get that the variance of x is the sum of the variances of the x sub k's. K goes from 1 to n, which we know to be a sum of the following numbers: p minus p squared. We're taking up the number p minus p squared n times, so you get n times p minus p squared. Or if you like, we get n times p times 1 minus p, which is the formula we got for the variance using a completely different approach way back when we studied the binomial distribution. This is a much easier argument. So I think this is really nice. Okay. Okay, so I want to talk now about the correlation coefficient. This is a number which measures the relationship between a pair of random variables. So let's assume in what follows that the variances of x and y, two random variables, are both not zero. Okay, so let's define the correlation coefficient as follows. It's called rho of xy. It's the covariance. It's a fraction. The covariance is on the top, and on the bottom is a square root. And what is the square root? It's the variance of x times the variance of y is in the square root. So this is like a kind of normalized, it's a kind of normalized covariance. And it has, in some sense, better properties. Normalized in the following sense. So it has the following properties, which I'm going to list now. Okay, so the first property, which is extremely important, is that so -1 is less than or equal to the correlation coefficient is less than or equal to 1. So it's always a number between -1 and 1. Okay, so we say that x and y are uncorrelated if rho of xy is equal to 0. So this is the term uncorrelated. And since we know covariance vanishes for independence, we know that x and y independent implies x and y are uncorrelated. Okay, so now I'm gonna save the slide and talk about the main property I want to talk about for the correlation coefficient, which is this. Let me save the slide. So main property is this. Well, let me first do an example. So let's let y equal a plus b times x for some constants a and b. Then let's compute the correlation coefficient rho of xy, which we saw by definition was the covariance of x and y divided by the square root of the variances of x with the variance of y. Let's compute what we have here. So first of all, what is the variance of a plus b times x with itself? What is the variance of a plus b? That's the covariance of a plus b times x with itself. And if you expand it out, you'll get, using the bilinearity property, you'll get the covariance of a with a plus the covariance of a with b times x plus the covariance of bx with a, and lastly, we add covariance of bx with bx. Now, each of these terms is computable, so let me just give you the answer. The first term is 0, the second term is 0, and the third term is 0. Just go back to the definition, you'll see it's 0. And this last term is going to give me b squared times the covariance of x with x. In other words, b squared times the variance of x. Okay, so that's the variance of a plus bx. Now, what is the covariance of x and y? Well, that's the covariance of x with a plus bx. And this also, by bilinearity, breaks up as the covariance of x with a plus the covariance of x with bx. And again, the first term vanishes and the second term becomes the b times the variance of x with itself. The variance of x, not with itself. Okay, so what is rho of xy? Well, we know what rho of xy is now. So rho of x, y, where y is in the box above, is going to be given by the numerator we know is b squared times the variance of x, and the denominator is the square root. What's in the square root? The variance of x times times the variance of y, and we know what the variance of y is b squared times the variance of x. And I made a slight mistake here. There's a b in the numerator as done because of what I did on the previous line. So there's a b times the variance of x. Well, anyway, if you do the simple algebra, this becomes 1. So we saw that if y is a plus b times x, the correlation coefficient is 1. Actually, that's not quite true because it depends upon the sign of b, right? If b is negative, you'll get -1. So the answer is plus or minus 1. So if there's a linear relationship between x and y, then between x and y, the conclusion is that the correlation coefficient is plus or minus 1. Okay, so actually the reverse is true, and the converse is true, and here's the statement of the fact. So here's the theorem, which I'm not going to prove, is assuming that the variance of x and the variance of y is not vanishing, then rho of xy is plus or minus 1 if and only if there's a linear relationship. So if and only if y is equal to a plus bx for some a and b constants. Okay, so in other words, the correlation coefficient detects linear relationships between the variables. This is an extremely important thing in statistics where you have two random variables and you want to know if there's a connection between them. For example, cigarette smoking might be the incidence of cigarette smoking in the population and the incidence of lung cancer in the population. The two random variables, we'd like to know how they correlate to each other. And this is actually something you would like to compute, and this is actually the number you would be computing there. Okay, that's it for today. So I believe we're done with section 7.4.